Okay, so I want to prove a much more difficult theorem now. This is known as Peirce's law. This proof is actually fairly difficult, but it illustrates some good principles. I'm going to run through it fairly rapidly to keep the time a reasonable length. Our main connective here is a conditional, all right? So whenever we're trying to prove a conditional, we start by assuming the antecedent of what it is we're trying to prove. So we're going to assume all of this for purposes of conditional introduction and try to show that this is going to follow at the bottom of that subderivation. So we assume all of this, and we're trying to show that the consequent is going to follow. So what do we do now? This is where this gets a little bit tricky, all right? A lot of people, obviously we have to make another assumption. We can't get directly from here to here. What a lot of new students are tempted to do is to assume the antecedent of this, okay? Now, it's not really clear where that's going to take us. And this, what we're trying to prove, our goal is not a conditional. We want to assume the antecedent when our goal is a conditional, like we did here. It's not really going to get us anywhere in this case, where what we start with is a conditional. So a better strategy here is to do what we did in the last example and assume the negation of what it is that we're trying to prove in this subderivation. So we're going to go ahead and assume not P. So we're going to assume not P, show some kind of contradiction follows, and from that we can conclude P. All right? Now this is where this gets a little hard. It's difficult to see what kind of contradiction we're going to get in here. But one idea is to see if we can get if P then Q as well as not if P then Q. And it should be fairly obvious that if we assume if P then Q, is going to get us into trouble right away because we can get P from that and we already have not P. And maybe we can get if P then Q because we already have not P, so P and not P will be a contradiction, and you can get anything from a contradiction. So maybe we can get both if P then Q and not if P then Q. So let's go ahead and take a look at that idea. So first let's try to get not if P then Q. So we'll assume if P then Q for purposes of negation introduction. So that gives us P from lines 1 and 3 in conditional elimination. Okay. And now we can reiterate not P into that subderivation. Now we can go ahead and close out this subderivation. You know, this got us into a contradiction. So not if P then Q. From lines 3 through 5, negation introduction. So now we want to go ahead and show the opposite And the idea here is fairly simple. Setting it up in to make every step explicit in logic is a little bit more complicated or a little bit more time consuming. But so to be clear, what we're trying to do is get the opposite of this. We want if P then Q. So we have a contradiction with line 6. So we're going to assume that P for line 7, we want to show that Q follows from P. Now, how can we do that? Well, we can't use this. This is in a different subderivation, and we can't use this. This isn't a sentence on its own. It's the antecedent of another sentence. But we do have a contradiction here, right, with the assumption of this big subderivation here. So what we want to do is assume that not Q, for purposes of negation elimination, and we're just going to reiterate lines 2 and 7 into this subderivation. Those will be our lines 9 and 10. And then line 11 will be Q by negation elimination. Lines 8 through 10. Okay. And finally, line 12 now will be conditional introduction, lines 7 through 11. And our line 13 now, we've shown that not P led to the assumption of not P led to a contradiction. So on line 13, we can conclude P by negation elimination, lines 2 through 12. Negation elimination. And finally, now we can close out the subderivation we started with, and we've shown that we can conclude this. We can conclude Peirce's law, lines 1 through 13, negation introduction.